Bismillahirrahmanirrahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Dear student, in the last two videos, we have been discussed the sketch of root locus by making use of two methods. One is pertaining to primitive method, in which we have calculated the roots of a second order system with the help of a coordinated formula, and here we have applied the different values of k, the entire positive range of the controller, which is the range of RL, and for the entire negative range of the controller, which is the range of CRL, and with the help of their respective calculated roots, we have sketched the corresponding root locus of a given system. In the second method, we have make use of properties, and we have observed that these properties these properties help us in a easier manner to sketch the root of a given system, as well as the advantage of these properties is this: by using these properties we are able to sketch the root locus for a lower order system as well as for the higher order system. I hope that you people really enjoyed that segment, and now I am moving toward to give you more pleasure of the root locus. Now here we go. This is the another problem that we are going to solve. The number of queries are, first of all, we have to sketch the complete root locus in the entire range of the controller, that is from minus infinity to plus infinity. It involves the CRL as well as the RL. The other queries are the range for the system stability, the controller gain, for an overdamped response, the controller gain; for a critically damped response, the range of the controller; for an underdamped response, as well as we also identify whether the given system can be designed as oscillator. If it is designed as oscillator, then what would be the frequency of oscillation? Here is the block diagram. Is the block diagram of a unity feedback system. Is the transfer function of the plant. Here we also compared the given system with respect to the problem we already solved earlier. In this system, this is the transfer function of the plant as well as controller is also involved here. The transfer function of the plant is 1 over S into S plus 2. Here the transfer function of the plant is S plus 4 divided by S into S plus 2. So here the only difference is the insertion of zeros in the left side of the poles that we have already discussed in the previous problem. So the open loop transfer function is the product of the transfer function of the forward element and the feedback element. So here the transfer function, open loop transfer function, is equal to k times into S plus 4 divided by S into S plus 2. If I am excluding here k, then the remaining transfer function is said to be G1S H1S. In this open loop transfer function, the number of finite zero is 1, the number of finite poles are 2. Now here we go to start the properties. The property number 1 is k is equal to 0 point. The k 0 points lies at system poles. So here the system poles are at S equal to 0 and S is equal to minus 2. The next property is equal to k is equal to plus minus infinity point. The k plus minus infinity point lies at system 0. So here we have one finite zero, therefore 1k is equal to plus minus infinity point lies at minus 4. As we have already discussed that for a rational function the number of pole and zeros must be equal. So if the number of finite zeros are not equal to the number of poles in the expression, means the rest of the zeros are at infinity. So I have written here the second zero is at higher values of s, like infinity here. The number of branches are equal to the degree of characteristic equation or the number of poles in the open loop transfer function. So here we have two poles, therefore the number of branches are 2. As we know that each branch has a start point from k is equal to minus infinity, then the branch goes to k is equal to 0, and then finally proceed to k is equal to plus infinity. Therefore we must know 2k0 point as well as 2k minus infinity point and 2 plus infinity points. Here we have a missing information about the second plus minus infinity point, because 1 plus minus infinity k plus minus infinity is lies on -4. The rest, the second plus minus infinity point is where we have to find out, and this can be find out by making use of property that we will discuss later. So please stay tuned with me. The next property stated that the entire root locus is symmetric with respect to real axis and with respect to the axis of symmetry, and we will observe that after the sketch of the given root locus in this problem, the final root locus sketch will come out to be symmetric with respect to the real axis and with respect to the axis of symmetry. Next property is the number of asymptote. We have to find out the number of asymptote. In our case here, the number of n, the number of finite pole is 2, the number of finite 0 is 1, therefore it is come out to be 2. Therefore we have to find out two asymptotes. The angle of the asymptotes can be calculated by making use of formula of theta RL and theta CRL. Theta RL gives us information about the k is equal to positive infinity, which is the end point of a branch, and theta CRL gives us information about k is equal to minus infinity, which is the start point of the branch. And we have already discussed that we have missed one information about the k minus infinity and k positive infinity, which comes out to be from by using these two properties. In this property we have to place the value of h. The value of h can be find out by making use of this expression. What would be the last value of h in this expression? We should have to start from 0, and the last value would be from this expression is n minus m minus 1, and we know that here we have n is equal to 2 and minus 1. Therefore in this expression we have to use just one value, which is 0 here. So if I am placing 0 here, the theta RL comes out to be 180 degree. Theta RL comes out to be 180. Oh, there is some mistake. This is the information about theta RL. Is the angle of theta RL. Theta RL is 180 degree, and if I am placing at 0 here, then theta CRL comes out to be 0 degree. So one start point of a branch would be from 0 degree, and one end point of a branch would be at 1 degree, and one start point of a branch would be at -4, and at -4 there would be the end of a branch as well. And there are two k0 point, which is s is equal to 0 and -2. So next is we have to find out centroid, the value at the real axis, from where we have to plot the angle 0 and 180 degree. And it is quite obvious that in the real axis 0 degree and 180 degree would be at the right side of the S plane on sigma axis, and would be at the left side of the real axis in the negative side of the real axis. When we have two angle of asymptote, then the centroid information is not very useful for us, and we can say that it is the redundant information. In this case, if there are 4, 6 or 8 angle of asymptote, then this centroid of information is important, because it is the point where we have to plot all these angles, and it's the point where all the asymptotes will intersect each other. After reaching centroid, it would be better to start sketch of root locus. First of all, we have to map pole and zeros. In our case, the poles are at 0 and -2. Okay, the poles are at 0 and -2. So the poles are at 0 and -2. And what would be the value of control gain here? Here the control gain is 0. So we have two K0 points. I would like to save this image for use in next time. So we have mapped the pole. Now the zero is at -4, and 0 is the point where the controller gain is plus minus infinity. So again, come to the root locus plot. The next thing is to map system 0, and where the controller gain is equal to plus minus infinity. Here we have two asymptotes. One is at 0 degree. So one asymptote belongs to CRL. It has 0 degree and 0 degree on sigma axis. So and it k minus infinity, and it is the start point of the branch. So at minus degree, we have the inverted arrow is the start point of the branch, and it is directing toward the system root locus. And the another one is sk is approaching to positive infinity, is the asymptotic, is the angle of asymptote of RL, is the end point of the branch. So I am representing the branch in the outward direction. It is the end point of the branch. Thereafter we have to apply the another property is the entire root locus on the real axis. So start from this side, take a point, a search point, and count the number of pole and zeros in the right side of this point. If the count comes out to be 0 or even, means the particular point or the particular search point lies on CRL, or the particular section lies on CRL where the controller gain is negative. So here my count is 0. So therefore this search point is on CRL, or my count is still 0 till this pole in the right side of this search point. Therefore the entire real axis on the right side of the S plane belongs to CRL. When I move to afterward this pole, ahead of this pole, my count comes out to be 1. If my count is odd number, if my count is odd number, 1 3 5 means the point lies on RL. My count is 1, my count is 1, my search point lies on RL. After this pole, once again my count in the right side of the search point is again even number. Therefore the right side of the search point, the number of poles are 2. Therefore the search point lies on CRL. This particular section portion belongs to CRL. When I'm moving here, now my count in the right side is 3, 2 poles and 1 0. My count is 3, is odd number. Therefore this section lies to RL. So I have marked the CRL and RL portion on the real axis. Now I am going to sketch the root locus. One branch starts from this minus infinity, and the another branch starts from this minus infinity, and this branch first of all must go toward K0. branch starts from minus infinity, the entire trajectory of the branch is from minus infinity to 0, and then k 0 to positive infinity. It is the range of CRL and it is the range of RL. Okay, so first of all, consider a branch from k minus infinity to 0. This branch starts from minus infinity moving on along the real axis, because this particular portion of the root locus belongs to CRL and its covers to this k0. The second branch starts from minus infinity. Definitely it will go towards 0 because it is the range of CRL. The arrow should be like this one. Okay, this branch after 0 moves from 0 to positive infinity, therefore this branch should move along the real axis, so therefore the arrow should be like this one, and the another branch after covering this 0 should move in this direction, so therefore the arrow would be like this one. It means these two branches will meet at some point, and then definitely these two branches will depart in order to cover their positive infinity. This branch should depart at some point on the real axis where the k is maximum with respect to the existing values of k on this particular portion of the real axis. So we have to find out breakaway and break-in point at what particular value of s this branch will depart, and what would be the value of k at that point. This branch should depart in the complex plane and then move toward their positive infinity, and the positive infinity basically lies on the real axis. Therefore these two branches should come on to the real axis again. Similarly be the case of the second root or second branch, and the second root would be in complex conjugate form, therefore forming symmetry about the real axis. As we have said earlier, the entire root locus is symmetric with respect to real axis. These branches once again should meet on the real axis, therefore we have to find out the break-in point. We have to find out one breakaway point and one break-in point. After this break-in point, one branch cover this positive infinity and the another branch will cover this infinity. So this would be the tentative sketch of the root locus of a given system, and for a complete sketch we have to find out the breakaway point and the break-in point. So once again I have to save this picture for any further use in the future. Okay, now make use of the property pertaining to find out the breakaway and break-in point. So here is the property to find out the breakaway and break-in point. As we have discussed that we have to differentiate the open loop transfer function without k, g1s, h1s with respect to s, and equate the derivative of the differentiation equals to 0. The polynomial comes out to be s square plus 8s plus 8, and the solution of this polynomial is minus 1.172 and minus 6.828, and if the solution of this polynomial is real one, then we have to accommodate these 2 points in our root locus. We cannot discard any real solution of the polynomial comes out after the differentiation, in order when we are going to find out the breakaway and break-in point. As I have stated earlier, the relation must be incorporated in our root locus, because these are the system roots as well. So we have to accommodate these 2 points, or one solution is minus 1.172, as we already obvious that we have a need of a one breakaway point in between 0 and minus 2, and that would be this one, and that will be this one. And another break-in point we are expecting after minus 4 at somewhere, and this would be minus 6.828. Next we can find out the controller gain on this point. So the controller gain on these points comes out to be 0.343 and 11.315, and this is the condition on magnitude. Here I have placed the I have replaced S by the solution of breakaway and break-in point. The solution comes out for finding the breakaway and break-in points. This is the required image of the root locus. Okay, now let's come to the queries for this particular problem. The number one is a part is the range of the range for the system stability. Here we can see that this is the second order system, and we must have information about the two roots at each and every value of k. If we are considering the negative range of the controller, then at each and every value of k, one root will be at the left side of the S-plane, because here because we have one CRL on the left hand side where k is ranging from minus infinity to 0, and one CRL on the right side of the S-plane. So at each and every value of k, one root will be in the right side of S-plane, and one root will be on the left side of S-plane. Therefore the presence of one root in the right side make the system unstable. Therefore we can say that the system is unstable for all negative values of k. Okay, now considering the positive values of k, which is the range of RL, here we can see that one branch starts from k0 and ends at positive infinity. The another branch starts from k0 and ends at another positive infinity. These two branches will remain in the left side of the S-plane. Therefore the system is stable for all positive values of k. Therefore the answer of part A, the system is stable for this particular range. The next query is the controller range for an overdamped response. We know that this for an overdamped response, the root must be real and distinct. For stability range from 0 to positive infinity, one should start moving from here, the another root start moving from here. These two branches meet at this point where S is equal to 1.17. So at this particular way, this root would be equals. Therefore for real and distinct roots, the value of the controller must be greater than 0 and less than the value at this point, and we have already calculated this value here at S equal to minus 1.172. the controller range is 3.43. therefore the answer is k should be greater than 0 and less than 0.343. We also can see from here that once again, when the root locus enters in the complex plane, re-enters in the sigma axis, once again the two roots will be equal, and after that the two roots will be distinct. One root will move toward this positive infinity and the other root will move toward this positive infinity. Here is the arrow should be in this direction. Okay, so one root will be moved in this direction because is the point where the k is approaching toward positive infinities, and the other root will move toward this positive infinity. So once again the root will be real and distinct. So we can say that the value of k, which belongs to minus 6.8, is 11.315 if the controller gain is greater than this one and less than positive infinity. If the controller gain is greater than this one and less than positive infinity, the root will be distinct. One root will be here and the another root will be here. So the complete answer will be this one. In this range the root will be real and distinct, and in this range the roots will be real and distinct. The next query is the controller gain for a critically damped response. For a critically damped response, the system root should be real and equal, and we can see that at s equal to this and s equal to this, the two branches meet with each other, therefore the roots will be real and equal. The controller gain on these values are k is equal to 0.343 and k is equal to 11.315. Therefore the answer for the critically damped response should be k is equal to this and k equal to this one. The another query is the range of the controller for an underdamped response. For an underdamped response, the root should be complex. Here we can see that after departure the root will be complex in complex conjugate form. So the controller gain pertaining to this value, if the controller gain is higher than this one and the controller gain is lower than this one, the root will be the roots will be complex. So the answer of this query will be the k greater than this one and less than this one, because in this range the controller gain will be complex. The next one query is at what value of the controller gain the system would behave like an oscillator, and what would be the frequency of oscillation. In this picture it is evident that the root locus is not crossing the imaginary axis, because it is the axis where the sigma is 0. If the root locus will cross the imaginary axis, if sigma is 0, its transient response will never diode. This system will remain to oscillate, and the point of intersection will give us the frequency of oscillation. So in the stability range the root locus is not crossing the imaginary axis, therefore this system cannot be designed as oscillator and there is no frequency of oscillation. Therefore here the answer is the given system cannot be designed as oscillator because it is not crossing the imaginary axis, and here omega n is 0. Okay, now let's move to the another excitement and another pleasure with respect to the root locus. Here is the another problem, and here we can see that is the OP loop transfer function of the given system is k upon s into s plus 2 into s plus 5. Once again, if we compare this OP loop transfer with the first problem, in which we have two poles, one is at s equal to 0 and the other one is at s equal to -2. In this case we have inserted one more pole in order to observe the dynamics of the system. When we have inserted one more pole in the left side of the previous problem 0 -2, here I have inserted one more pole in the left side of the these two poles. So this one is the characteristic equation. The degree of the equation, the degree of the given system is 3, because the characteristic equation has the highest power 3. By inserting one more pole, we have increased the degree of the system, or the degree of the characteristic equation. In this case the value of m is 0 because we have no finite 0. The number of poles are 3. Therefore when I am applying the property number 1, k 0 point, the k 0 point lies at system 0. The system zeros are at 0, -2 and -5, and k plus minus infinity point in the absence of 0 means this k plus minus infinity point lies as at infinity and infinity at higher values of s, because k plus minus infinity point lies on system zeros. If there is no finite 0 means these points are lies on at higher values of s. In this system we have 3 branches because the degree of the equation is 3, the number of poles are 3, and I'm again repeating here, each branch has a start from -infinity. The branch then reach to k 0 and then finally proceed to k plus infinity. So here we have missing information, all 3 positive infinity and all 3 negative infinities, where we have information about only k 0 point. So we have to find out 3 minus infinity point as well as 3 positive infinity point in order to start a branch and in order to and a branch. Therefore, when I am applying the number of asymptote, it comes out to be 6. 2 into 3 minus 0, n is 3, m is 0, means 3 positive infinity and 3 minus infinity make a total of 6. These are the 6 missing information, and which can be find out by finding the angle of asymptote. So theta RL basically give you information about k positive infinity. The formula is this, and similarly the formula of the theta CRL is this. For in order to find out the location where k is equal to minus infinity point lies, in this formula we have to apply the value of h, which starts from 0, increment by 1, and the final value is n minus m minus 1. Here we have 3 poles, none of 0, minus 1 means 2. Therefore here we have to apply 0, 1, 2. When we have applied these values in two formulae, the theta RL comes out to be 60, 180, 300, and similarly theta CRL 0, 120, 240. And from where we have to draw these angles, then we have to find out centroid. Centroid is sum of poles minus sum of 0 divided by n minus m. We have poles at 0, minus 2, minus 5. We have no 0 here, therefore n divided by 3 minus 0 means number of poles minus number of 0. Therefore the centroid, the point where this angle has to be drawn, is about minus 2.33, and we know that the entire root locus is symmetric. Okay, now here we go. We have to draw our root locus. First of all, we have to map our poles. One pole is at 0, the another pole is at minus 2, and the third pole is at minus 5. Okay, is minus 5 here and minus 2 here and k0. These are the points where the controller gain is 0. So here the controller gain is 0. Then we have to draw the centroid at minus 2.33. Suppose the centroid, this point correspond to minus 2.33. Therefore I have to draw here an angle of 60 degree. If I am proceeding this line, this would be 240 degree, and if I am measuring angle 120 degree with respect to the real axis, if I am proceeding this one, this would be 300 degree. So making this straight line, we have all angle. The angle of CRL is 0 degree. K, where k is approaching minus infinity. The second angle is at 120 degree. Okay, second angle. And the third angle is at 240 degree. Here k is approaching to minus infinity. So here the root locus is asymptotic with respect to their asymptotes. One CRL is coming from here, the another CRL is coming from here, the arrow is inverted, and one CRL is coming from here. So 0, 120 degree and 240 degree is the start point of CRL, and the end point of root locus is the end point of RL as well, is 60 degree. Here the branch will go to its end, the k approaching to positive infinity here. Other one is 180 degree. With respect to this centroid, is positive infinity here, and another positive infinity is here. One branch will go to its end. Here k is also approaching to positive infinity. Now make use of another property, the CRL and RL on the real axis. Once again, select a search point and count the number of poles and 0 in the right side. The count is 0 means here is the CRL. If my count is 0 or even number means this particular portion belongs to CRL. Beyond this pole, my count is 1, is odd number, therefore this particular portion belongs to RL. And then my count beyond to the second pole is again even, means this particular portion is CRL. And again my count is 3 with respect to this search point in the right side, therefore this particular portion belongs to RL. Okay, fine. Okay, we have to start CRL first. Minus infinity is the start point of first branch. It starts from minus infinity and covers this 0. The CRL will remain on the real axis because this particular portion belongs to CRL. One branch start from 120 degree because the angle of asymptote suggests is the start point. From here the root locus is asymptotic with respect to asymptote. If one branch is coming from here, the another branch basically is the conjugate root also coming from here. They should cover their respective 0. 1 0 0 is already covered by this CRL, so this branch should come on the real axis in order to cover their 0 which are on the real axis. One branch will cover this 0, the another branch will cover this 0. This branch after covering this 0 will move toward their positive in infinity, means one branch start from minus infinity, cover the 0 and goes to its positive infinity. One branch has a complete trajectory over here. The second branch moves from here, cover this 0 and further move on this direction. Okay, fine. The first branch already arrive at here, then further move from here. They should meet at some point, then would depart, and after their departure they must go to its positive infinity. They must go to its positive infinity. So what are the information we have to find? Number one is the breakaway point, the second one is the break-in point, and the third one the imaginary axis crossing point. So first of all I have to save this picture if we want to use further. Okay, now I am moving to find out the value of the breakaway point, the break-in point, and the imaginary axis crossing point. We know that the breakaway point can be found out by differentiating the open loop transfer function and equating the derivative equals to 0. Then this would be our polynomial after the differentiation, and the solution of this polynomial comes out to be real. As we already expected, we have a need of one real solution over here and one real solution over here, and I have also stated if the real solution is the outcome of the polynomial of the breakaway and break-in point, then we have to consider this solution. We cannot discard this solution. By using these two solution, finally the root locus comes out to be this one. One breakaway point is at minus 0.88, the another breakaway point is minus 3.78. so this branch comes from minus infinity, and the conjugate branch comes also comes in the complex plane, and both branch meets at minus 3.78. Similarly, when these two branch moving on the real axis, they meet at point this one, and after they depart for their positive infinities, they must cross the imaginary axis omega, because the angle of asymptote also suggests at higher values of s the root locus is asymptotic with respect to their asymptote. Therefore we have to find out the imaginary axis crossing point, at what particular position the root locus will cross the imaginary axis. Okay, now let's move to find out the imaginary axis crossing point. point. This one is the characteristic equation, is given in our problem, by equating 1 plus gs hs is equal to 0. We have this polynomial. By completing the Routh array. First, by completing the Routh array, we have to consider the first column only and apply the condition such that all the sign of the first column should be positive. Therefore, the first condition is this: the value of k must be greater than 0 in order to have a positive value here. And with respect to s of power 1 rho, the first term is 70 minus k divided by 7. This term should be greater than 0 in order to have a positive value here. If we have all the positive value here in the first column, means we have no sign change, which means we have no root in the right side of S plane, because number of sign changes suggests the number of root in the right side of S plane. So by solving this term, the value of k comes out to be less than 70. So the range for the stability comes out to be 0, greater than 0 and less than 70. Okay, in order to get the imaginary axis crossing point, we have to formulate the auxiliary equation. That auxiliary equation we could be write down from the preceding row of that row which has all zero element. So if I'm applying here k is equal to 70, the first element will be 0, the second element is already 0, the rest element are all 0. So therefore we can write down the auxiliary equation from here. What would be the auxiliary equation? 7 is the coefficient of s square plus k, and k with s of power 0, because if the first term has s square, the second term has a power which is decremented by 2. Therefore we have the auxiliary equation 7s square plus k, which is equal to 70, equals to 0, and from here the value of s comes out to be 3.16. By applying this all values in our root locus, the imaginary axis point comes out 3.16. The value of k is 70. In this way we have completed the root locus. Okay. After we have sketched the root locus, now come to the query of this problem. The first query is the range of the controller for system stability. Here we can see that we have 3 branches here. Each branch starts from minus infinity. One branch starts from minus infinity from the right side of S plane. The 2 branches start from their minus infinity, which are on the left side of the S plane. Means at each negative value of k, 2 roots are in the left side of the S plane and 1 root in the right side of the S plane. Therefore the system is not stable for the entire negative values of k, because the entire negative range is on the right side of S plane. Then for positive values of k from 0 to positive infinity, we also here can observe that 1 root will remain in the negative side, but 2 of the roots after their departure will move toward the right side of the S plane at this point where the value of k is 70. Therefore here we can say that the system is stable for k greater than 0 and less than 70, because beyond that the root locus will move in the right side of the S plane. This is the range for system stability. The second query is the range of the controller gain for an overdamped response. For an overdamped response, the system root should be real and distinct. So in this case, one root is moving from here, the second root is moving here. When the roots will meet at here, the value of both the roots will be equal. This is the condition for system critically damped. For a critically damped response, before this the root will be distinct. So at S equal to minus 0.88, these 2 root will be equal. So we can say that when k is greater than 0 and less than 4.06, these 2 roots will be real and distinct. So the answer for overdamped response is k greater than 0 and less than 4.06. When k is equal to 4.06. These two roots are equal, therefore is the condition for a critical damped system. And when k is greater than 4.06, the roots are complex and enters in the complex plane. And finally, at before this point, the system is stable and the response, we can say that is underdamped. Therefore the range for system underdamped response is should be k greater than 4.06 and less than 70. When k is 70, the roots are pure imaginary. Here the sigma part is 0. The decay rate here, the decay rate is 0. The system natural response will never die out. The system will continue to oscillate. If you design a system at k is equal to 70, the roots will be pure imaginary. The system will continue to oscillate. The frequency of oscillation is 3.16 as we have calculated earlier with the help of Routh stability criteria. So here we can say that the system can be designed as oscillator when the gain k is equal to 70. The frequency of undamped oscillation is 3.16. Here we can say, here the system can be said as marginally stable. When I am answering these queries, I am considering only those roots which are closer to the origin. These are the two roots which are closer to the origin. These roots are said to be the dominant root, and these roots are having the impact on the system natural response. The third root is far away from the origin. Its sigma is more negative than these two roots. Therefore the transient with respect to this root will die out very rapidly. So this root will not affect on the natural response. Only the dominant root will affect on the natural response. Therefore I am answering all the queries with respect to these two roots only. Now let's compare the problems we did so far. In the first problem, we have just two poles, none of zeros. We have observed that the system is stable for the positive controller ranges, which is from 0 to positive infinity. When we have inserted in this given system a 0 in the left side of the S-plane, we observe that the trajectory which is straight here, making an angle of 90 degrees with respect to real axis, is bent toward the left side of S-plane, and here on all increasing value of k, now the sigma becomes more negative, so it makes the system dynamics even more faster, because a higher negative exponent means the decay rate is faster than before, which is sigma value is -1, is constant here for all increasing value of k. And when we inserted the pole in the left side of S-plane with respect to this particular given system which we have solved earlier, we observe that now the trajectory of the root locus bend toward the right side of the S-plane instead of bending toward the left side. Now the trajectory is bending toward right side, and here on all increasing value of k, the sigma become less and less negative, which makes the transient slower. So insertion of zeros in the left side of a given system bends the trajectory toward right side and make this system transient response slower, and the trajectory finally crosses the imaginary axis, and beyond that the system would be unstable. But in this case, when we have inserted a 0 in the left side of the first problem, which bends the trajectory to the left side of the S and make the transient response faster and make the system more stable. So this is how the compensation works in the control system. Student, this is another excitement. I hope that you will enjoy a lot. In this problem, one task is to sketch the complete root locus, another task to find out the system stability from the given root locus diagram, and then we have to design the system in order to keep the overshoot under 20% limit, and with respect to this given information, we have to design the system, find out all possible route, and finally we have to write down the system complete response when the system is subjected to unit in step input. And with respect to the design operating point, finally we have to find out the peak time, the rise time, the setting time with 2% error criteria. Okay, now here we go. This is the given system. This is the block diagram of the given system. Is the unity feedback system. GSH is the open loop transfer function. Here I have excluded k, therefore the transfer function can be abbreviated at G1 H1s. Next is the system characteristic equation. 1 plus GSH is equal to 0. Here the system highest power in this expression is S of power 4 base. The system is of fourth order, or the degree of the characteristic equation is 4. Now next we have to apply the property in order to sketch the root locus. K 0 point, the K 0 point lies at 0, -4, and these are the, and remaining 2 is the factor of this term, -4 plus J4 and -4 minus J4. Next property is K is equal to plus minus infinity point. We have no finite zero here, means all these zeros are at infinity, where the system has positive or the negative infinity value. Third property is the number of branches. The number of branches are equal to the degree of characteristic equation or the number of poles. So we have 4 poles, or the degree of the characteristic equation is 4. The number of branches are also 4. The entire root locus is symmetric with respect to the real axis. Now here we have to find out the asymptotes. We have 4 finite poles, no zero here. Therefore we have to find out 4 asymptotes. We have to find out 8 asymptotes, 4 asymptotes for finding the minus infinity points, and 4 asymptote to find out the positive infinity point. Therefore this can be find out by using the theta RL for k positive infinity point, where they lies, by using this formula. Similarly with the case for CRL, and here we have to apply the value of h. The last value of h should be n minus m minus 1. Therefore 4 minus 0 minus 1 is 3. Therefore we have to apply in this formula 0, 1, 2, 3. After applying this value, the angle comes out to be 45, 135, 225 and 315. Similarly the theta CRL 0, 90, 180 degree, 270 degree, and from where we have to apply these angle. For that purpose we have to find out centroid. Centroid sigma is equal to sum of pole minus sum of zeros. Here I am using only the real part, because if I am applying here the imaginary value, then positive J4 and minus J4 will cancel each other. Therefore either we have to use imaginary value here, or you are not using imaginary value here. This will not change your answer. Sigma is -3 here. From -3 we have to plot all these angle. Therefore here is the root locus plot of the given system. First of all we have to map all the poles. One pole is at 0, the another pole is -4, the third pole is -4 plus J4 and -4 minus J4. After mapping the pole, then with the help of centroid, we have also I have also plotted all the angle of asymptotes. Here is 45 degree for RL, is 135 angle for RL, and is 225 angle, and is for 315. These are the angle for RL. Therefore I have marked here k positive infinity, k positive infinity, k positive infinity, and k positive infinity. Here these are the point where the trajectory will go to their ends, and what are the starting point is the k minus infinity points, which are the angle of asymptote. We have already determined for CRL is k minus 0 degree, plus 90 degree, 180 degree and 270 degree, and I have marked with k approaching minus infinity here. So these are the starting point of the branches. Next is the we have to find out the root locus on the real axis. From this point, the right side, there is no pole here, no, the number of pole and zeros count is 0, therefore this segment correspond to CRL. Now my count is 1, so this segment is correspond to RL. Now my count is 2 in the right side of the S plane. So this portion of the real axis again correspond to CRL, and as we already marked here, k minus infinity and k minus infinity, which confirms our distribution on the real axis as well. So one branch start from here, cover this 0, one branch start from here, cover this 0. Further, these two branches move on RL with this direction. They should meet at some point, and we have to find this point by using a property, the breakaway and break-in point. So breakaway and break-in point for this case is applicable. We will find it later. Now consider the third branch. The third branch start from here and cover this 0. These two 0 already covered by these two branches, so this branch covered this 0. The fourth branch is the conjugate of the third branch. In the same way will cover this 0, and their asymptotic angle suggests that the asymptotic angle for the RL suggests that the branch further move in this direction in order to cover its positive infinity, and this branch will cover this positive infinity. So these two roots are in complex conjugate form and forming symmetry with respect to the real axis. Now here what information we have to find out. One, in the breakaway point, we need here one real breakaway point and the imaginary axis crossing point. So here we go. Breakaway and break-in point, we have differentiated. The open loop transfer function is the third order is the third order polynomial. After solving, we have find one real solution and two complex solution, and as I have already stated that the real solution must be the breakaway and break-in point, the complex solution not necessarily the breakaway break-in point. So here in this case, this real solution is the breakaway point 1.7. we already needed this one because in between k0 and k minus 4 these branches should meet with each other, so they meet at this point. And the complex solution we have to discard because these 2 points are not the system root, because there is no possibility of the other any two branches which should meet in this root locus. If we want to confirm whether or not these two branches are the system root or not, we have to apply this S value in the characteristic equation. If real value comes, means these are the system root. If a complex value comes, means these are not the system root, so we have to discard this two solution. Next is the imaginary axis crossing point. In this characteristic, by using this characteristic equation, first of all we have to complete the Routh array, and we know that the first column is important for system stability. In this column we must have all the positive signs, so I have applied the condition here. This value must be greater than 0, and this value also must be greater than 0. Therefore the solution comes out to be k greater than 0 and less than this one. So therefore this is also the range of system stability as well. Again, by writing the auxiliary equation from the preceding row, where we have find out the maximum range of stability. If I am applying k this one here, this would make S1 first element of S1 is 0, the second one is already 0, the third one is 0, therefore the entire row is 0. So with the help of the preceding row, we can write down the auxiliary equation, and by placing k equal to this, the roots comes out to be 3.26, means this is the value of the j where the root locus crosses the imaginary point. And at this value, if we design the system, then the system will behave like an oscillator, and the frequency of the oscillation is 3.226. Therefore we have plotted the root locus by making use of all this information. Our next target is to design the root locus which will ensure a 20% overshoot, which will be given here in the problem statement. Okay, we have to design a system in order to keep the overshoot that must not exceed 20%. So now let's work for 20% overshoot. First of all, by making use of this formula, we have to find out zeta, which is 0.46456. We know that the angle phi is equal to cos inverse to zeta. We have discussed earlier, which gave us the angle information 62.8 degree. In a given root locus, we have to draw a line which makes angle with the negative real axis 63 degree, which intersect the given root locus at a point. The point of intersection give us roots that will ensure a 20% overshoot. S1 is the first root and its conjugate is the second root, and we can write down the coordinate of this root with the help of the graph paper on which we have plotted the root locus. Here I am giving you one advice, that we should have orthogonal scale on x and y axis. Same unit on the x-axis and same unit on the y-axis in order to have a good or a better shape of the root locus. So with the help of the graph paper, the coordinate of the S1 root can be determined. So here I have written the coordinate of these two roots, which is minus 0.7 plus minus j2. Here is the diagram once again. You can see here is the diagram. So these are the coordinate minus 0.7, and this one is the value of j, this one is the value of j. Here I am taking j2. So these are the two roots. These two roots are closer to the origin, so therefore I have written here these two roots are said to be the dominant root. Now we have to work for remaining root. In our system we have the degree of characteristic equation equals to 4. We have the fourth order system, therefore we have to find out two more roots. Here I have the question thing, how roots are remaining. Two roots we have find out, therefore the two roots are still remaining. How we are able to find out the remaining two roots? Here is the simplest way to find out the remaining two roots, by using the Grant's rule. It has some restriction. Either we cannot apply this Grant rule, or we can apply Grant rule if the degree of the denominator of the GSH, open loop transfer function, the degree of the denominator of the open loop transfer function must be at least 2 times greater than the degree of numerator. So please check whether in our problem we have fulfilled this requirement or not. The degree of the denominator is 4, the degree of the numerator is 0. Therefore here we can apply this rule very much easier, in an easier manner, which is stated that the sum of poles of GSHs is equal to the sum of the roots which we are designing, which we are going to find out at a particular design specification. So the poles are at so the poles of the given system are at 0, -4, -4 plus j4, and -4 minus j4. Here either we have to write down the imaginary part, or we have if we don't write down the imaginary part, it doesn't affect in our answer, because the negative because plus j4 and minus j4 will cancel out each other in every case. So the given poles of the open loop transfer function equal to the roots of the newly designed system. Two roots we have already find out, minus 0.7 plus j2, minus 0.7 minus j2, and two roots are remaining. So I have write down plus sigma, because the imaginary terms already cancel each other. So we can get only the information about the real part of the roots. Here sigma comes out to be minus 5.3 by using this information. Minus 5.3, we again go to our given root locus. Suppose if this point represent minus 5.3, then we have to uh, uh, we have to we have to so by making use of this sigma, the remaining two roots can be determined by using the projection from this point onto the root locus. So so the coordinates of these two remaining roots can be determined by using the graph paper. After finding the coordinate of remaining two roots with the help of sigma which we have find out with the help of Grant's rule, then we have to find out the controller gain k at these roots. We have used here the value of 1 of root because in all the four roots the value of controller gain will remain same. So here the control gain comes out to be 16.65. Then we have to write down the control ratio for the design system. We have already discussed in page number 8 of the root locus document. If the system is of unity feedback, then its forward path transfer function can be written as gs is equal to n1 over d1, and by placing this value in the control ratio, the final control ratio expression comes out to be n1 over n1 plus d1. In n1 basically is the numerator of gs, and n1 plus d1 is the root and is the system characteristic equation. So in our case we have k in the numerator, and the value of k comes out to be 16.65, and in the denominator I have placed all the rows which we have find out with respect to the given specification. By placing here the input information as well, and then thereafter by taking the inverse Laplace transformation, these control ratio the complete response can be calculated, can be determined easily. It is your task, you have to find out by yourself. I have already uploaded shared you a PDF document with you in which I have explained how to calculate, how to take the inverse Laplace transformation of a given transfer function in S domain. Next is to find out the other time responses. Here is the formula: Tp is pi over omega d, Ts is 4 by sigma. For 2% error criterion, Tr is pi minus 5 by omega d. At the dominant root, we have to find out all these things from figure, from the graph paper. At the dominant root, the omega d is 2 radian per second, sigma is 0.7, and phi is 63 degree. So these three time responses can be determined easily. So it is also a task for you. You have to calculate all these time responses. I have to make one correction here. Think how many roots are remaining, because this angle phi will give you the information about the two dominant root. Then what would be the remaining root? The answer will come from the order of the system, or the degree of the characteristic equation that we have used in the first place of this problem, where the degree of the equation is 4. Therefore, when we have find out two root, means the two roots are still remaining, and that two remaining roots could be find out by using the Grant's rule. Is one of the way. If Grant rule is not applicable, then how we would be able to find out the remaining two roots? I am leaving this query for the live session. You have to quantify all unknown terms in this expression: a0, a1, the angle phi 1, a2, the angle phi 2, and the value of these time responses is your task, and you have to share your answer with us. Thank you very much, and thank you very much for sparing your time. Stay safe. Allah Hafiz.